How to design PCR primer. In this video, I will discuss about the various properties of the PCR primer and the method to design it. So first of all, I will discuss what is the PCR primers. It is a short single-stranded DNA sequence which help in the amplification of DNA during PCR reaction by providing free 3'OH region to the tagged DNA polymerase to initiate the amplification and also during the elongation step of the PCR reaction. So, primer is the very important component of the PCR reaction in addition to the tagged DNA polymerase, DNT pitch, PCR buffers and template DNA, which together helps to complete the PCR reaction. PCR reaction occurs in the three steps as we know very well, that is denaturation, annealing and extension step. So, primer binds to the complementary DNA sequence during the annealing reaction. So, primer should have the annealing temperature between the 55 to 65 degrees C so that it could bind specifically to the single-stranded complementary sequence. In PCR reaction, during PCR reaction, the primers used are DNA primers, unlike the in vivo replication, that is replication occurring normally where RNA primers are used. RNA primers are involved. Then the question arises, why DNA primer is used in the PCR while RNA primer is involved during in vivo replication? So, the answer is DNA primers are more temperature stable than RNA primers because during PCR reaction the first step is the denaturation which occurs at 94 degrees C. So the primer must be more temperature stable so that it could not get degraded at this high temperature. Then the next point is during DNA polymerization in PCR, which is a unidirectional step, so there is no chance of removal of short RNA primer after the polymerization is completed if RNA primer is used. That is, and also the tagged DNA polymerase doesn't have the proofreading activity also. So, as we know during in vivo replication, DNA polymerase 1 helps in removing short RNA primer after the completion of the replication, while this property doesn't have the tagged DNA polymerase doesn't have this property, so DNA primers are used here. Now comes the properties of the PCR primers. The first and most important property is the annealing temperature of the PCR primer. The annealing temperature is the temperature at which primer binds to its complementary sequences. That is, when during the denaturation step, both strands of the DNA get separated, and during the annealing reaction, at the annealing temperature, primer binds to its complementary sequence of the single-stranded template DNA. So, the annealing temperature is very important parameter during designing a DNA primer. Annealing temperature should be 5 degrees C lower than the melting temperature, and melting temperature is calculated using the formula 4 into GC content plus 2 into AT content of the sequence. An ideal annealing temperature must be 56 to 65 degrees C. Variation in this range causes or affects the PCR amplification. If annealing temperature is too low, then the primer can bind to any of the complementary sequence and gives a non-specific result. Thus, primer cannot bind if the annealing temperature is too high. So, it must not be too low or too high, as it can give the non-specific result. Now, another property of the primer is the length of the primer. Primer are the short sequences, generally 18 to 23 nucleotide long primer, always gives the best result. Short primers less than the 18 base pair do not have the affinity to amplify properly. While if the primer is too short, annealing temperature also becomes very low and it reduces the amplification capacity. And in case of long primers, it is not recommended because annealing temperature becomes too high, which also leads to the non-specific binding. However, long primer is highly specific in long range PCR. Now comes to the GCA content of the primer. How much GCA content should be there for a good primer? So during designing the primer, GCA content is very important parameter. GCA content between 40% to 60% is acceptable. The annealing temperature of the primer between 55 to 65 degrees C with 50% GC content performs better. If GC content is too high, at given annealing temperature, primer will mismatch with other sequences and GCA rich sequences are highly non-specific. The chance of non-specific amplification in GC rich region is very high as compared to the AT rich region. So GC content should be between the 40% to 60%. It is critical to understand if 8 to 10 bases of primer will match with other sequences and the annealing temperature is too low, it definitely amplifies the DNA, but it gives the false result. So the next property is the complementation in forward and reverse primers. The forward and reverse primers must not be complementary to each other. That is, both forward and reverse primer do not match with each other, it should be kept in mind, and are not complementary with each other. Otherwise, instead of binding with target sequences, both primer, that is forward and reverse primer, will bind with each other and will create a dimer. More than 4 complementary bases and lower annealing temperature induces dimer formation. When primers bind with each other instead of binding with the target sequence, it creates a dimer, and dimer can easily be amplified in PCR because it is shorter sequences of up to 50 to 60 base pair and will give the false result. Next property must be kept in mind, that is repeat bases in primers. Repeated bases can bind within the primer and makes primer non-active. So if some of the dinucleotides or trinucleotides are repeated in primer, it binds within the primer and creates a hairpin loop and make it inactive or non-active. More specifically, if repeat bases are present on the terminal end of 3'-in, it will create a serious problem during the PCR reaction. Now, how we can design the PCR primers by keeping these properties in mind? So, first of all, identify which gene or DNA fragment we want to amplify. Identify that sequence and obtain it from the NCBI. Now go to the Primer 3 software, which is open access and freely available primer designing tool. Copy and paste the sequence from the NCBI in the box given in the Primer 3 software. Now select the options for forward primer and reverse primer in the first and third box below the box where the sequence has been pasted. The sequence from the NCBI which has been copied and pasted in the box. Below the 3 options are there, forward primer, then in the middle it should be for selecting the probes, and in the third box it is selecting the reverse primer. So select only the first and third box. Never select the option given in the middle because we want to run the simple PCR. Hence we do not need a probe. Now after clicking the forward and reverse primer, click on the pick primer button and wait for the result. Analyze first the result window. Now you can see that the parameters like the length of the primer, GC content, annealing temperature and hairpin formation all are under the standard criteria, and then you can use these primers for your PCR reaction by ordering it to the company, which will provide you according to your sequence, and then you can use it for your specific PCR reaction. Thank you.